circuit that involves a resistor and an inductor. Now, the values that you have for your resistor, we've only got the resistance value. Here we have 57.1 ohms, which coincidentally aligns with what we can get out of our lab volt workstation. For the value of inductive reactance, for the inductor, we've got 85.7 ohms. The applied power, we have an AC power source and we have an applied voltage of 110 volts AC. One of the things as we work through finding the values in this circuit, I also wanted to take an opportunity to be able to show people and demonstrate that voltage and current, the relationship between them at different points of the circuit, specifically at the power supply, they're going to be out of sync with one another. The sine waves here across the resistor, the voltage and current relationship are going to be in phase, and we're going to prove that. As well as here across the inductor. According to our textbook, the voltage and current relationship should be about 90 degrees out of phase. And we're going to take an opportunity to show that and demonstrate that. So we're going to go through the entire process of solving for the missing values in the circuit, both for the power supply, the missing values here for the resistor, and the missing values here for the inductor. Now, to make sure that we can differentiate, I've put a subscript, meaning the voltage drop across the resistor will have an R, and any of the values associated with the inductor will be identified with an L. Values associated with the entire circuit will be with a T, meaning total. I'm going to be using a red magic marker so we can differentiate between the given values in our circuit and those that we're going to calculate through this process. Our starting point is going to be to find the impedance for the circuit. I have a given value of resistance and a given value of inductive reactance. Our natural start point will be, let's find circuit impedance. I'm just going to move over here and we'll start doing the work. Our first step will be to calculate circuit impedance, or in this case, Z. When we look at the relationship inside of the circuit, we have two components. One resistance, denoted by the letter R, one of inductive reactance coming from the inductor, and it is identified by X sub L. Now, if resistance and inductive reactance are 90 degrees out of phase with one another, then that means that we can use trigonometry and the hypotenuse. So right here, this would be your impedance, or Z. So impedance. Impedance is made up of two components, but they're not equal. We're going to use trigonometry. So the formula for impedance, or Z in this case, is equal to R squared plus X sub L squared, and then we're going to do the square root. In this case, following, and I'm going to input our values that were given to us. We had 57.1 ohms squared plus 85.7 ohms squared. Now, we can punch this into our calculator, and the result should be And the result should be 102.98 ohms. Now, it bears note that one of the standards in the electrical program is in all of our calculations, we will always round to 2 decimals. So here, we will round it down or up, as the case may be, to 2 decimal places in order to maintain accuracy. I'm going to go and take this value and input it into our chart over here. And then we're going to move on to step 2. I've gone ahead and I've put down the values we've just calculated for step 1. Now, of the values we have, I can actually use Ohm's law to calculate for the total amount of current for the entire circuit. Now, what's more important is one of the rules that govern a series circuit. In Ohm's law stipulated that the current in a series circuit is the same at all points. This is really convenient for us because by finding the total amount of current for the circuit, I can actually use that value now and input it in the rest of the equations, and we'll make the process of solving for our given values very easy. So I'm going to go and set up, and we're going to go to step 2. Now in step 2, we want to find the value of circuit current. That means we're going to use Ohm's law. In this case, if I want to find I just cover up I would take the applied voltage and the resistance, or in this case, the impedance, because of the fact that resistance, inductive reactance, and impedance is always measured in ohms. It's a simple matter of substituting the R for the Z. So why don't we do that? We're going to substitute the R for a Z because it is measured in ohms, or units of resistance. It acts like resistance, it behaves like resistance, we calculate it like it was resistance, and so we can substitute the R for the Z, and in this case, to find the value of circuit current, so I total, we're going to take the applied voltage, which is E total, and we're going to divide it by the value of impedance. Inputting our values that were given to us, 110 volts, divided by 102.98 ohms of impedance. We're going to type that into our calculator. I'm just going to steal my little cheat sheet. And I total should be 1.07 amperes. Now again, this is a value that has been rounded to 2 decimal places. Let's go and input that into our chart, and we're going to keep moving on. Moving on to step 3, we're going to find the voltage drop across the resistor using the previously calculated value of current that we just did in step 2. Now, we're still using Ohm's law. I've gone ahead and I've drawn out Ohm's law's triangle, and we can see that if I want to find the value of the voltage drop across that resistor, it's simply going to be a matter of taking the current and multiplying it by the resistance of the resistor. In this case, our formula is going to look like this. The voltage drop across the resistor will be equal to the current multiplied by the resistance. And the values we've calculated previously, .07 amps, that was rounded, multiplied by 57.1 ohms. Type that into a calculator, and the answer should be 61.1 volts. Again, this is a value that has been rounded to 2 decimal places. I'm going to go and input that back into our chart, and we're going to move on to step 4. Involves calculating the true power consumed by the resistor. I tend to work where I've already calculated the voltage drop across the resistor, and I find it far more efficient that I still have this value in my calculator, that I'll proceed to go to step 4, calculating the power, because I only have to input one other value. In this case, right now, we're still using Ohm's law, but it's changed a little bit. We're calculating power. And power, if we look at this, we are going to take the voltage drop across the resistor and we're going to multiply it by the current of the resistor. And so that formula is going to look an awful lot like this. P is equal to ER multiplied by IR. We start to input the values that we have, which in this case was 61.1 volts multiplied by the current we found, and that was 1.07 amps. Punching that into the calculator, we should get for a total of 65.37 watts. Watt, because that is considered to be true power. I'm going to input that into the chart, and we're going to keep moving on. We're moving on to step 5, finding the voltage drop across the inductor. We're still using Ohm's law. The only thing that has changed is the subscript, that right now we're looking at E sub L, meaning the voltage drop across the inductor, and if we look at it, we're hiding this. It's going to be the current across the inductor multiplied by the value of inductive reactance. And that gives us this formula right here. Using our given values, or pardon me, calculated values, 1.07 amperes multiplied by the value of inductive reactance, which happens to be 85.7 ohms, and the voltage drop is going to be 91.7 volts. Now, if somebody's looking at this and they're going to think, I had an input of 110 volts, we've just calculated that the voltage drop here is 91.7 volts, but I know that the sum of the voltage drops in a series circuit should equal that of the applied voltage. That is normally true, but when we're dealing with composite circuits, meaning we have a circuit that has both an inductor and a resistor, things don't add up nice and neatly, and this is the reason why we have to use trigonometry in order to solve for these values. So we're going to move on. I'll input that value and we'll be right back. On to step 6, calculating the amount of reactive power that is going to be consumed or used by the inductor. We're still using Ohm's law. The only thing that is different here is that we've substituted the value of P for the value of VARs. VARs is reactive power, but it is still power. We still calculate it in the same manner. And that's going to give us the following formula. VARs L is equal to the voltage drop across the inductor multiplied by the current of the inductor. Using the voltage drop we've calculated previously, as well as the current, 91.7 volts multiplied by 107 amps, 1.07, pardon me. That gives us a total of 98.12 VARs sub L. And we're going to go and input that into our chart. When it comes to calculating the apparent power for the entire circuit, there are two acceptable methods of doing this. One, we could use the simpler method, which is Ohm's law, or we could use a trig calculation. I'm going to perform this both ways because I want to prove that the math works out no matter which way we do this. And you will see that there is a very, very low margin of tolerance in terms of, are the numbers out? Yes, they'll be out by like less than 0.02%. It's extremely accurate. Ohm's law. How do we find apparent power? Well, apparent power is VA, and we are going to use the applied voltage for the entire circuit, so E total, multiplied by the current for the entire circuit. In this case, 110 volts multiplied by the 1.07 amperes. That's going to give us for a total of 117.7 VA, and of course this is rounded to 2 decimal places. Now, our second method is to use a trig calculation. The apparent power is equal to, if we take the true power squared plus the reactive power, which is var sub L squared, and square root. Inputting the values we've calculated previously of 65.37 watts squared plus 98.12 vars sub L squared. Putting this into a calculator, you will get 117.90 VA. So you can see that you have a very, very close alignment of the two formulas, and if anything, it's just because of the fact we've rounded these values as to why they're not perfect. But certainly they are acceptable. And so I'm going to be using this formula. And I'm going to input this value into my chart. Now that I've calculated the apparent power for the circuit and I've got it inputted here on my board, all that remains is to solve for the power factor in the circuit, which is the measure of a circuit's efficiency, as well as angle theta. So these will be steps 8 and 9 respectively. And we come to step number 8, calculating the power factor for the entire circuit, or in other words, the value of efficiency in the circuit. Electric circuits do suffer from power being drained, and so we have to calculate how efficient a circuit is. Now, personally speaking, I've always remembered it as being the ratio of true power to apparent power, and that is how I personally will calculate it. Are there other formulas available to allow us to calculate power factor? Consulting your textbook, you will see there is a whole host of different formulas that you can use. This one works for me, and I've been teaching it like this for quite a while because I tend to not get confused. I like to apply the KISS principle, keep it simple. And so the ratio of true power to apparent power, so we can express that as the following formula. Power factor is equal to P divided by VA. We're going to input our values. 65.37 watts divided by 117.90 VA. It bears to note that power factor is expressed as a percentage, and so what we're going to have to do is we're going to have to multiply this by 100 in order to express this in a percentage. Putting these values into a calculator, the value you should be getting on the calculator will be 0.558717,948. Obviously, you're not going to be writing that down, but I just wanted to reconfirm that we're also going to round to 2 decimal places, and we're also going to multiply it by 100 in order to have an expression as a percentage. As a result, your power factor for this circuit should be 55.87 because the next value is 1, so we're going to round down. And power factor is 55.87% efficient. Not very good, but as we progress throughout this semester, I'll be showing you tips and techniques of how to improve the power factor in a circuit. I've gone ahead and I've added the value of power factor, which we've calculated at 55.8% efficiency, and now we're going to calculate for angle theta. Step 9 is our final step, and it involves finding the value of angle theta. In the textbooks, I don't think it's covered well, and I like to mention that what angle theta is we're trying to find the amount of phase angle difference that exists between the voltage and current waveforms. Yes, the current waveform can be seen using an oscilloscope as well as the voltage waveform. If we built this circuit that we've got here up on the board and we're using all these calculated values, it stands to reason that if we actually built this circuit, I've got to be able to measure and look at the voltage and current waveforms, and that will tell me whether or not I built the circuit accurately. So angle theta is actually a very important value in that once I've built the circuit, it would allow me to verify if I've built the circuit within tolerances, if I see that I have the correct amount of phase angle difference. Now, phase angle difference, or angle theta in this case, in the textbook it says cosine of angle theta is equal to power factor. Now, you have to use this value. If you're like me, I do the power factor calculation, and I will multiply this just mentally. I don't actually calculate it using the calculator because I'm used to doing it. But I will retain this number in the calculator because in my step 9, I know I'm going to calculate for the angle theta. And you're just going to use the power factor value, not the percentage, but the actual decimal value here. But there's one thing. We actually have to manipulate this formula a little bit, meaning the cosine of angle theta, well, cosine's got to come over here. So angle theta is equal to the power factor multiplied by the negative cosine. So it's simply a matter of taking this value of 0.5587, and then I'm going to use the negative cosine function in my calculator. So negative cosine, and if you've punched this into your calculator, you should get, for a value of 56.03, and that is going to be expressed in degrees. Now, I've already gone ahead and I've built this circuit in real life using our LabVolt workstation. What I've done is I've actually built the circuit that we've seen on the board using the values found in the chart for the inductive load module as well as for the resistive load module. I've taken the time to calibrate the output of the variable power supply for 110 volts, and I've got this set up through a display up on the board so that we can see how accurate things are when we've done the math compared to real life. Now people will see that here I'm measuring the voltage for the entire circuit. This is the voltage drop across the resistive load module, the voltage drop across the inductive load module, and then what I've done is I've taken, we have the ability to look at the apparent power for the circuit, the true power for the circuit, as well as the reactive power, as well as power factor. Now, I'll bring to your attention I've tried to calibrate as close as I could to the nominal voltage that we found in our calculations of 110 volts. The current is pretty close. It's not exactly that close to the 1.07, but we're in the neighborhood. The only thing that's a little bit disappointing here was that the voltage drops are not very consistent. We're seeing about a 10 volt difference from the calculated value to the actual value, as well as right here I've got about a 7 volt difference. Now there's a couple of reasons why, to what I attribute there being a difference. I want people to remember that inductors that you work with in real life, as opposed to what's on calculations, are not perfect. And what I mean by that is inductors inherently have a certain amount of resistance. They are coils of wire, and as a result there is no such thing as a perfect inductor. Now the calculations are pretty good, and you can see that there is a slight discrepancy. And again, I don't have the ability to fine-tune the value of resistance. I took a reading. It was not 57.1 ohms, it was 56 ohms. Unfortunately, with the inductors, we can't measure inductive reactance. We can only calculate it. So my ability to fine-tune the amount of inductive reactance is fairly limited. So this is why we see that the voltage drops are not exactly what we calculated, but the trend is there. You'll see that the voltage drop across the inductors is much larger than that across the resistive load module. And if you'll see, what is interesting is that the apparent power that we calculated was 117.9 VA. Well, we're here at about 111 or 112, but that the watts, or the true power consumed by the resistive load module, was about 68.7 when we calculated 65.3. As well as over here, we calculated for 98.12 VARs sub L. Well, here the reactive power is a little bit less, attributing to maybe the fact that we have a certain amount of resistance, and that throws out what's going on over here. And the same applies to the power factor. Yes, the power factor, there are such devices that exist that allow us to measure power factor. While it may not be common on a multimeter, they do exist. And you'll see, again, it's not expressed as a percentage, but as a decimal. And I believe we had calculated a power factor of about 55, so we're out by about 5%, which it's not bad. But this only tells part of the story. I want to go and look at it through an oscilloscope. So I'm going to be right back, and I'm going to switch this view from a meter view to that of an oscilloscope. Here we have the circuit represented by a couple of waveforms on the oscilloscope. Now, down below, and I don't know if my students can see this or the viewers can see this, but the yellow sine wave represents the voltage for the entire circuit. Now right here, the RMS is 110, but if you're looking at it, right now it's 50 volts per division. So if I was to look at it, this is 50, 100, 150, and a little bit more. This is the peak. So we're not seeing a waveform that is RMS, we're seeing the peak. And as such, the RMS or the peak of 110 is probably going to be about 160. Same thing with the current. The current is represented by this pale blue waveform, and it's showing at 1 ampere, but if we look at it, it is set at 0.5 amps per division. So I've got 0.5 plus 0.5 is 1 amp, and not exactly a full amp, maybe 1.4, but this is the peak of the current sine wave. What you're seeing here is the time base, and what this represents is the amount of phase angle difference that exists between the current waveform and the voltage waveform. This is the important thing of why we've done some of these calculations, specifically angle theta. I also would like to overlay the voltage drop. So this is the current, if it can stop moving, as well as this yellow, which is the input voltage waveform. Now I'm going to turn on the third channel over here, the waveform, which is the voltage drop across the resistive module. I'll be right back. What you'll see in my cursor, I'm going to channel 3, and I'm going to turn on the voltage across the resistive waveform. Now, what's really interesting to me is in the textbooks we've heard that the voltage and current in a purely resistive circuit will be in phase with one another. And here's proof positive. The fact that the current waveform for the circuit and the voltage waveform across the resistive module, they intersect at point 0. That means that they both rise together, peak together, and collapse together in unison. This is what is meant when they say that the voltage and current are in phase with one another, is that these two waveforms. Now the difference in the peaks is attributed to the value. Now we calculated the voltage drop as being 61 volts, so if this is 50 volts, we're in that neighborhood. Remember that this is a peak value. Now I've got a third or fourth waveform, if you will, depending how you're looking at it. I'm going to overlay, and that will be the waveform for the voltage drop across the inductive load module. And let's do a comparison and see, because if across the resistive load module, voltage and current are in phase with one another, and according to our textbook, in an inductive circuit, it's purely inductive, the voltage and current are going to be 90 degrees out of phase with one another. Now, how do we explain that? If this is a series circuit, the current is stationary at any point within the circuit, and as such, the current does not move. It is the waveforms that have to move in relation to that. So what we would say is that the voltage lags the current by 90 degrees. That's what we think, but let's prove it. I'm going to go turn that channel on. I'm going to channel 4, and I'm going to turn the input for E3 on. And we have all 4 waveforms. The first one in blue represents the current. In yellow represents for the entire circuit. In purple represents the voltage drop across the resistive load module. And in red, this represents the phase angle difference between the current and the voltage across the inductive load module. And if I can get a straight edge, we can see right about here that there's almost 90 degrees of phase angle difference from the peak of this to where this intersects on the zero plane. There's almost 90 degrees. Now, why did I say almost? This is due to the fact that I mentioned earlier, these inductors are not perfect inductors. They have a certain amount of resistance, and as such, you're not going to see a perfect 90-degree phase angle difference. Through traditional forms of testing, we've always asked students to describe the voltage and current relationship to make sure that people understand how the circuit is going to react when we throw in different components. In this case, when we start asking a student, could you describe to me what is the voltage and current relationship across the resistor bank? Now, because this is a series circuit, I've gone ahead and I've drawn in a sine wave to represent the current, and I always use red for current. Current in a series circuit will be the same at any point within the circuit, and as such, it is the voltage waveform that must change in relationship to it. But when we have a resistor bank, it is said that voltage and current are in phase with one another. So what we're going to do is we're going to draw that relationship. And if they're in phase with one another, that means then that the voltage waveform is going to start at the exact same point. It's going to climb in unison. It will peak in unison. It will start to collapse, cross over at the exact same point on our scale, and we will repeat the process and the negative alternation. We're also, if a student was drawing this in pencil, they would be required to identify each of the waveforms so that a faculty member, when they were grading their work, could understand what they're looking at. If it's all in one color, it makes it a little bit harder. So we're going to identify this, and we're going to put down E, or voltage. And we're also going to stipulate that voltage and current are in phase with each other. Now, this is what we would like to see on a test. People tend to take shortcuts and just put V and E are in phase. I won't accept that as an answer, or I will be giving minimal points for that. We want to see it written out in longhand, fully explaining what we're looking at. Now, we're also going to look at what about the phase angle difference. How much phase angle difference do we have between the voltage and the current? In this case, we could say that angle theta is equal to 0 degrees. Looking at the voltage and current relationship with an inductor bank, again, I have the exact same template. I've written in the sine wave and identified it, but now we want to look at how does the voltage react with the current? Remembering that, we should write this down. Inductors naturally oppose a change of current. So based on that very fact that an inductor naturally is going to oppose a change of current, that means then that it's going to kind of hold back that voltage waveform. And we know that the phase angle difference is 90 degrees. The question becomes, do I start the waveform down here or up here? Well, if the current is at 0 and an inductor opposes a change of current, that means that the voltage is going to lag the current by 90 degrees. So when this is at 0, the voltage waveform is going to be at peak, but in the negative alternation. That means I'm going to start from about here, because here is 180 degrees. Right about here would be 90 degrees. Over here, 270. So if I'm lagging by 90 degrees, that means I'm going to start in the peak, negative alternation. The voltage waveform is going to cross at 90 degree interval. It will peak when the current is at 0, and then it will collapse and cross at 90 degrees offset and continue on. And again, we are going to identify, if you're using the same color pencil or pen, you must identify that this is a voltage waveform. And if your test instructions do stipulate to explain that relationship, remember that it's going to be the proper use or the proper context to explain that your voltage lags the current by 90 degrees, and we should also stipulate in a series circuit. So there you have it. On tests, we normally will attribute a certain percentage of points on calculations based on this. Due to the fact that if a student makes a mistake on their calculations, that error tends to carry forward. But if a student can show they have a grasp of the overall concept, that has some merit, it has some worth, and as such, I will always break down my tests to this type of a component as well. So let's move on to the last section, which is, let's look at the voltage and current relationship for the entire circuit. I'll be right back. Finally, we're going to look at the entire circuit. Now, we calculated that the angle theta was 56.03 degrees. So that is the amount of offset or phase angle difference between the voltage and the current. Remembering that in the series circuit, the current is stationary. As a result, I've still got that red sine wave. It hasn't moved since we've done any of the other demonstrations. So what we have to do is we want to try and be as accurate as possible. Angle theta is 56.03 degrees. Well, if I break this down, a full sine wave is 360 degrees, half of it is 180, a quarter is 90 degrees. I break that in half again, I get 45. Well, I know that I'm somewhere in between the 45 and 90. The midway point is 67.5 degrees. So without measuring it, I would estimate or guesstimate at this case that right here, halfway between 67.5 and 45, if I was to try and represent this with any degree of accuracy graphically, remembering as well that this is an inductive circuit, and so because of this 56 degrees, the voltage is going to lag behind the current. Again, that means that I'm going to draw the voltage waveform and the negative alternation. I'm going to start here. Now, it's not going to be exactly 90 degrees. I'm going to kind of start off something like this, and then that means then it will peak somewhere over here. And then start to collapse exactly in the same direction. Trying to be as accurate as possible, but the trend is wherever they cross, I should see a lagging sine wave. So there's your degree of offset. Same thing over here. And we are going to identify it as E or voltage. And we're also going to explain that for the entire circuit, the voltage lags behind the current. By an angle of 56.03 degrees. If you can give me that, that's probably worth a couple points on the test for the entire question. I hope you find this informative and it helps you through the process of doing these calculations.